Okay, so the tutorial is going to start, so please have a seat.
Good morning. Okay. Is it okay? Good morning, everyone. Thank you. We are happy to be here at the conference. We would like to thank the organizers for organizing this very, I think, unique conference, specifically on lifelong learning and continual learning. And it's really, for me at least, it's exciting to see the community grows and more young researchers coming to this field. So today we're going to speak about advances in continual learning theory. We will start by introducing ourselves. So my name is Itay Evron. I'm a student of Professor Daniel Sudvi at the Technion. I'm finishing my PhD now, and it is mostly focused on the continual learning theory and some generalization in neural networks. My master's was on extreme classification, which is by now not a very popular field, sadly. And next September, I'm joining Meta Research. I let my collaborator Jin introduce herself.
Hello, my name is Jinhua Li. You can simply call me Jin. So I'm a second-year student, PhD student, supervised by Andrew Sachs in UCL, together with SOBC and Gatsby unit. And I've jumped into this vast field of machine learning and deep learning to develop a identifiable contrastive representation learning for multimodal neuroscience data. But then now I'm mostly involved in a learning theory inspired from cognitive or computational neuroscience.
Okay, let's motivate ourselves. So like I said, continual learning is really a growing field, and I think it's becoming increasingly important with the emergence of LLMs and foundation models, and specifically fine-tune method. So people like to think about transfer learning as when doing fine-tuning, but I think that as models become more resource demanding, and people will start using more and more the continual fine-tuning. So they'll fine-tune every few, I don't know, hours, days, weeks, but we won't be able to actually do just one fine-tuning phase, one pre-training phase and one fine-tuning phase. It will probably be more continual. And for us, it's a good timing to be in this field. And at this point of time, there's already a considerable amount of continual learning theory, but still there's I think, a significant gap between the experimental findings and the theoretical findings. And generally, as theoreticians, I think that theory can shed light on existing empirical successes and failures, and we saw this happening in the overfitting phenomenon in deep neural networks, where initially we didn't understand anything, we didn't know why it works, like it seemed to completely contradict everything we knew from classical machine learning. But then nowadays we understand it much better, and also from implicit bias perspectives and so on. And another thing theory can do is to have a predictive value and to predict the behaviors of popular models and algorithms. For instance, by deriving scaling laws for how much data you need, how much parameters you need, and so on. And lastly, we believe that it can help improve existing algorithms, and we saw it happening in diffusion models, where better sampling algorithms were derived sometimes first analytically and then empirically. And maybe last but not least, personally, I think theory can be, first of all, very fun and very challenging. But if you're concerned, then also publishable. So there's a whole conference on continual learning now, but I think the general audience conferences like ICML, ICLR, NURI, SCOLT, they are very open today to publishing theory papers specifically on continual learning. It wasn't like that before, but now it's completely like that. And today is a good chance we are going to give a vast overview. And I think it's a good chance for theoreticians and practitioners to actually find new opportunities. Some notes. Our focus is going to be on recent advances in continual learning theory. We aim to convey the essence of recent techniques, setups, assumptions, and so on. Of course, we cannot cover everything in less than 2 hours. And as a result, some recent work is not going to be discussed. The perspective that we take is primarily a machine learning one from using statistical tools and optimization tools. We are going to show some math, but not too much because we don't want to burden you, and we want to keep it quite a broad overview than a deep overview. And we will be happy maybe to try to take questions throughout the presentation, but otherwise maybe at the end we'll have time. Okay, so maybe on another note on the perspective, as I said, we are taking a machine learning perspective, but other perspectives exist like cognitive sciences and areas like this, but we are focusing on machine learning. So the outline will be, we are going to give a quick intro on tools and assumptions and setups, like linear setting, mean field approach, linear neural networks, and then we'll try to discuss and understand maybe the phenomenology of catastrophic forgetting, like what's causing catastrophic forgetting and how it reacts to different factors of the networks and training. And then finally, we'll discuss algorithmic methods for remedying catastrophic forgetting, and we are going to try to say something on how we analyze these algorithms rather than just propose new ones. That's a different area. In between, we'll have 1 or 2 breaks, time allowing, because we want everyone to stay energetic and happy. So around, I think, 11:40, we'll have the first break. Okay. Yeah. So the main challenge that we all know is, at least until now, was catastrophic forgetting. And to illustrate it, let's consider a simple problem with 2 consecutive learning tasks. So we have the first task solution and the second task solution. And the simplest, really, I think, learning algorithm can be continual learning with SGD. So we start from some initialization point, let's call it theta 0. And then by using stochastic gradient descent or gradient descent, we minimize the loss on the first task until we have a solution in the set of the first task solution. And then we minimize the second task by starting from the previous solution until we have a solution in the second one. And like we see from this illustration, we kind of forgot what we already knew. So we are not, after learning the second task, we are not in the set of solutions for the first task. And this has been, so we call it catastrophic forgetting. It's the performance degradation on previously learned tasks. And so far it has been, I think, the central focus in continual learning. Research also analytically, but also empirically, but we focus on the analysis of this phenomenon. And I might, we might mention also the transfer, like another metric, which is the transfer, which we are also interested in, not only forgetting, but forgetting is the central one. Okay, the first chapter, as I said, is a quick intro to typical approaches. We'll start from linear settings, then mean field approach and linear neural networks. So linear settings. As theoreticians, we often start really from the simplest model we can find. And in continual learning, luckily, many continual phenomena already arise in very simple models and also in linear models, yet they are not fully understood in these settings still. Yeah, great. So, and another motivating area is all the NTK research area, the NTK regime. And we know from the NTK that under certain assumptions, neural networks exhibit linear dynamics. So for instance, neural networks that are infinitely wide or that have really large initialization scale behave kind of, they are approximated well by their linearization at the initialization point. And then they functionally follow a linear differential equation. So essentially, this means that if we really understand continual learning in linear models, it can help us understand deep models. And this has been like a main motivation, I think, in continual learning research, both empirically and analytically. And two very simple continual learning models that we can consider. The first is the regression model. We just predict using so x times the predictor w. And we can think about the classification, which we usually use the sign, but we can define exponential losses, logistic losses, whatever. And we'll try to kind of mention important differences between different setups. So some of these differences can be the data assumption. Some papers assume random features, some assume random labels, some assume noisy labels, some assume noiseless labels. And we will also mention the training method. So whether we train to convergence or just early stop, and whether we use regularization or not. So a first example, I think, shows why, we shows the usefulness of linear settings is shows that linear settings behave like a kind of they have a projective nature. So let's start by assuming regression tasks where we have this perfect, you can call it teacher or just offline solution. So if we see all tasks together, we can solve it linearly. So the labels are explained linearly by the features. And this is reasonable in noiseless settings or in when you are highly overparameterized. And again, back to this very simple scheme, we start from some initialization, let's say 0 initialization, but it doesn't have to be like this. And then starting from, we obtain the current solution or the current iterate by starting from the previous iterate and minimizing the current linear loss, squared loss of the linear model with SGD or GD until we converge. And then what happens, something interesting that happens mathematically, we showed in a CoLL22 paper that algebraically you get the closed form solution, which is, I think all of you are familiar with this solution for least squares problem from numerical algebra course. But then because we have this, we start from a previous iterate, not just from the 0 initialization, then we get this another contribution from the previous direction, from the previous iterate, which is orthogonal to the directions of the current task. And this, importantly, we never actually compute the pseudo-inverse. We just, we talk mathematically what happens. If you learn two convergence, then you get with SGD, what you get is mathematically equivalent to this closed form solution. Yeah. Exactly. Great question. The question was whether it converges so whether we can. You're questioning the practicality of this scheme, which is it's a good point. We never actually converge. To actually converge, we need to take t to infinity. So usually we do early stopping. I'm going to mention it later in the presentation. But at least mathematically, it's interesting to look at it like this. And if you kind of assume that you don't converge, but you obtain a low enough loss, then we expect the behavior to be quite similar. But yeah, it's good to keep in mind that we don't actually converge practically. Yeah. Sorry? No, I cannot hear you, sorry. I have to think about it. I'm not a Bayesian guy, but maybe let's talk about it later. Yeah, the question was how is it connected to, I think, the Bayesian rule, but I'll have to think about it. Okay, so this happens algebraically. And then geometrically, what we showed in the paper is that we can think about it as starting from an iterate, projecting onto the set of solutions of the first task. And then when we see the second task and we minimize its loss, we we project onto the set of solutions for the second task. And then we converge onto the set of solutions of the third task. And so this gives a geometrical interpretation, which also we found very useful, and as I will show later. So now we are going to the second part of this chapter on mean field approaches. Oh, sorry, yeah. Yeah, So because we converge and we assume kind of realizability, then you know that there exists there's a solution space which is non-empty, which so I'll show it. So for instance, for the first task, we know there exists a set of solutions that perfectly solve the first task. And what happens here, this is equivalent to just finding the closest point on this set, the point closest to the point on this set that is closest to the initialization. And when we solve the second task, we find the closest point on this set, which is closest to the previous solution. So we just keep projecting and onto these subspaces. Does this answer your question? Okay. The W1 is? Yeah, even I have difficulties hearing.
So how practical is it to assume that W1 star, W2 star, and so on lie in the space of W because you are limited by a linear approximator?
Is your question because we don't converge, or just are you asking about the assumption? Okay, so yeah, we can question the assumption. The assumption we make just to make things plausible and analyzable. But again, if you're in a noiseless setting, which theoreticians often assume, then it's completely, that's the assumption, and it happened. The set is non-empty, you have solution, and if you converge to a solution that perfectly solves the task. And then also, if you are highly overparameterized, even if you're in a noisy setting, this set will be non-empty. So you're going to get the W1 star or W2 and so on that perfectly solve the current task. Okay. So yeah, now we'll move to the midfield approach.
All right, so the next following two subsections about the mean field approach and linear neural networks, I will mostly talk about the learning dynamics. The reason why I specifically put those two approach among the many other methods that people use, that it's talking about the learning dynamics, which I think is heavily understudied in the field, because I think most of the studies that we have right now focus on the post-hoc configuration. So after the training, you look at the model and then you try to understand what's the performance, what has changed, and all these mechanistic interpretability tools about what's the model configuration. But I think a lot of questions around what happens during the learning hasn't been addressed a lot. And those are the two theoretical models that I am familiar with, which can give you some insights about those learning dynamics, and that's why. All right, so what is the mean field approach? So this is mostly inspired from statistical mechanics, and this is to describe a deterministic average behavior from the highly stochastic system. So give you an intuitive example is that thinking about this room as a system, and then you want to understand this room, but then you can think of like millions and billions of atoms of this room, but you cannot possibly describe all individual atoms' movement or its behavior. However, physicists came up with this order parameter, temperature, which can give you a good average dynamic of this entire system. And that's what I meant by a average behavior of the highly stochastic models. So our goal would be to find the temperature. And this is like a really just analogy, but like find a good order parameter of the neural network, which can give you a good understanding of how does the generalization network, for example, changes over the learning. All right, so to do that, people often use this teacher-student framework together. So teacher-students are basically two or more than two networks. So so I will give you a brief description of how this framework works in the next slide, but using this framework, we can make this learning dynamics problem of multi-layer networks amenable to analyze theoretically. And often the behaviors of these neural networks can be described with some sort of ordinary differential equations over time. And using this teacher-student networks, you can kind of came up with different learning setup that you're interested in. For example, here we're interested in continual learning. So maybe you can change the task similarity between two tasks by controlling the teachers. I will go into a little deep into it later. But again, this method also has common assumptions that people use, for example, high dimensional input, but this is often the case, and often the online SGD setup with the infinite data supply. And there are some architectural constraints if you want to have the solvable ordinary differential equations, but there has been lots of theoretical works in general of this approach to relax those assumptions. If you're interested, I can give you some references later. So what is teacher and what is student? So there's this confusion between different subfields of machine learning using the same term, but meaning different thing. And I think the teacher is one of those things. So I think there has been a lots of teachers in terms of knowledge distillation, which is pre-trained on certain task, and then you use that as a model. But here it's really kind of data generated model, which is a Oracle data. So you initialize the teacher network. You don't really have to train that. That's a teacher, which will gonna give you the correct label or the Oracle label to train the student. And the students will learn to generate basically the same label as teacher, teacher's output given the same input using the gradient descent. So let's think about the continual learning setup that we're interested in. So you can initialize multiple teachers, which will be a individual task, individual teacher network, and then you are going to have a one single student network. And then now for each task, you randomly sample one input X, and then you will going to do a forward pass on the teacher network, and you will get the labels, so the Oracle labels from each teacher, from each task. And then you are going to train this on the student by making a student prediction, and then do the gradient descent on the loss, whatever you defined. So again, the average case generalization dynamics will be described by the evolution of few order parameters. For example, the correlation between the teacher student weights, or the norm of the student weights, or the norm of the teacher weights, and so on. So for example, this is a one example plot.
I think we have a question, sorry.
In this setting, the student has no access to the weights of the teacher.
No.
Only to the labels.
Only to the input and the
Right,
label,
right.
yeah. But again, maybe you can come up with a learning setup where you have
Yeah.
that kind of a hint. But again, that's like a kind of flexibility that you were going to have with this setup.
But,
yeah.
but this is very different from knowledge distillation.
Yeah,
as you
exactly,
said.
yeah. Okay, so that's, for example, kind of a plot that you can get. Sorry, there's a typo. But basically what you can describe is this ordinary differential equation. And if you do the numerical integration over time, you will get exactly the same evolution of the generalization adder of the neural network that you train with the online gradient descent. All right, and a very short remark on the linear neural networks, because that's what we do during my PhD. So Zaks and colleagues have shown that deep linear neural networks can give you an explicit solution of the learning dynamics. And first of all, linear neural networks, I mean really linear neural networks without non-linearity. And why do you even care about those? The thing is, like, even though it's completely linear, people figured out that this can still exhibit some interesting nonlinear learning dynamics, which is universal in nonlinear neural networks. And still this gives you theoretically amenable method. So what I mean by nonlinear learning dynamics is that often if you train neural networks, you are going to see not a smooth learning curve, but often you will see a sudden loss drop, and then you are going to have a long plateau and again a phase transitions. And this kind of learning dynamics is still visible in linear neural networks, and then we can have a good insights on what's going on using this simplicity of the linear models. And this is a little different from the previous approach, because at least in this case, you are going to have an explicit solution of the time evolution. So you don't need any numerical integration that you have to do often with the mean field approach, which is another approach. And if you're interested, there are a couple of papers which studied specifically a continual learning on task similarities using these linear neural networks, but we're not going to cover those in our tutorial. By the way, there is a slide uploaded on the Slack if you guys want a detailed references and so on. Okay, so we were going to go into now, okay, what did we found using all those theoretical tools actually in catastrophic forgetting. And one thing, there are 3 points that we want to make. One is the task similarity, and the other is task recurrence and over-parameterization. And then I will gonna quickly cover task similarity before the first break. Right. So when I say task similarity, you might already have a good intuition or good feeling of, okay, what is the task similarity? But actually, to actually quantify or technically define what is task similarity, it is not, you can think of many different measures. For example, in Evron's paper, each task will be defined as a one hyperplane, and then the principal angles between different tasks, so different hyperplanes, can be a task similarity. You're going to have a orthogonal tasks or completely overlapping tasks or somewhere in between. And in teacher-student setup, you might think of it as an overlap between two or multiple different teachers' weights. So if you have a high correlation between the teachers' weights, it means that it's highly correlated, does very similar tasks, or it can be controlled completely orthogonal. But this task similarity is often easier to define in this some measure, quantitative measure, but then it is hard to really project onto the real world benchmark or data set that you can test different hypotheses, especially when it comes to recent large foundation models, and then you try to do the fine tuning on it or do fine tuning on certain tasks. How will you gonna define a task similarities on those previously entire pre-trained tasks and then a new task and the consecutive task that you want to fine tune on? So it's important, at least I think, for theoreticians to think about coming up with the task similarity measures and the definition, which we can actually bridge and project onto the empirical results that we see. So one of the good direction that I think is from Goldfarb this year. And here their definition of the task or different tasks was the random orthogonal projection of certain of the original task. And this nicely projects onto, for example, a benchmark of permute MNIST, because the number of the random projections that you do will be basically the number of different permutation that you do, and then you have a nice control of actual real world data set, task similarity, and the definition that you have. Right. And again, there are very different measures of this task similarity with different tools, but luckily we have a nice common conclusion from different approach, which is that the intermediate similarity is the worst for the catastrophic forgetting. So it's not the least similar ones or the most similar ones, but somewhere in between we're going to cause the worst forgetting, as you can see in this plot. But then it's not only about the task similarity. For example, again, this is the one that you can learn from looking at the learning phase, not only at the end of the training, is that this is time-dependent phenomenon. So if you look at the two panels on the right side or left side, there are two different relationships between task similarity and forgetting in different time points. And you can see at the end of the training, so when it's at its convergence, again, the forgetting is the worst in the middle task similarity, but this tendency is different when you are in the early phase of the training. Okay, so now we talked about the task similarity and how it affects with how it interacts with the forgetting, but then can we have some more understanding of what's the cause behind it? And the follow-up work from the Lee and the colleagues tried to explain it with the trade-off between reusing the node and activating a node using the teacher-student setup. So what is the reuse of the node and activation of the node? So let's say you train with the first task, and then there are certain neurons or units or nodes which get highly activated, and some are not. And then you have the next task, the second task coming, and then now the question is, okay, do I reuse the units that were learned before, or should I activate the new ones to learn about this task? And there is this trade-off that the neural network should deal with. And what you can see is when the task is completely orthogonal, the node importance, node similarities are 0, and then it kind of increases as the task similarity increases, but it's non-linear. It's not a linear relationship. So basically, in simple sentence, the task similarities brings different bias during the learning. In terms of trade-off between either reusing the node or activating the new node. And you can study this analytically during the training dynamics using this teacher-student setup. So I mostly talked about this task similarity and then how it affects the forgetting. But again, we already showed that this is a time-dependent phenomenon, a time-dependent function. And there are other factors too. So it's not an independent axis in this forgetting effect. So we will talk more about how does the task recurrence interact with this, and overparameterization, which is particularly interesting at this time point, how it interacts with the task similarity and its effect in the forgetting. Just note the paper from Lee and the colleagues from last year's CoLLAs and Zhao this year showed that the label noise level can also make the forgetting more critical for the dissimilar tasks. So there is another factor which affects this forgetting, which is the noise, basically. Okay, finally, so we can think of it as in different way, which is a loss landscape. And Mirzadeh et al. Showed that if you have a wider and shallower local minima of the tasks, it is prone to forgetting less. And also Mehta and the colleagues showed that pre-training, we're gonna make the minima shallower, and this leads to the better mitigation of the forgetting. And here is a nice illustration. What does it mean? So let's say you have a fixed difference between the two task solutions. So delta W is fixed between task 1 and task 2. But then let's say you got a loss landscape which is sharper in the left panel than the right one. Then as you move from the task 1 solution space to task 2 solution space, you can see that the forgetting is less when you have a shallower minima. But then this brings a nice intuition about this asymmetricity and task similarity. So here the task distance was the same, but depends on what kind of initialization you have, this task similarity will act differently, basically. So basically moving from task A to task B is different from task B to task A, even the task similarity itself is different. So we cannot think of it as just a scalar value, but it's the vector. You have a distance, and you need to think about the order that it's presented. And indeed, Bell and Lawrence showed that task ordering affects the forgetting. So you have multiple tasks, and then you can see different task similarity as the color map of the distances between the tasks. And you can choose the different paths, for example, minimum or the maximum path. And then if you look at the forgetting from the two different strategy, either you go through this minimum path or you take the maximum path. So exactly the same tasks, but different orderings, and that will cause the different level of forgetting. But one noticed that there is a high variance. So this again hints us that it's not only about just the orderings or the task difference, but interactions of a lot of things. Okay, so let me just close up with some of the future directions and open questions. So again, I think there should be more studies on the similarity notions, especially its possibility to breach into the real world data set and really compare it to the predictions from the theory and the empirical results that we can see if it agrees or not. And another thing is this multiple complicated interaction between many different factors, task similarity, ordering, and overparameterization, which nicely can be wrapped over this word curriculum learning. About this curriculum learning, shortly, there have been lots of questions if this actually matters. Does it actually matter? And in a lots of literatures, in a standard supervised learning setting, this doesn't really matter that much. For example, Wu and the colleagues show that the effect of the curriculum learning is kind of marginal when you do it on the standard supervised setting, except when you have a limited time budget or the data is somehow noisy. And also Manelli et al. Gives the analytical understanding why is that the case, and they try to understand it with the overparameterization, which is often the case in deep neural networks. So when you have overparameterized neural networks, you often have a pretty good chance of having a nice self-network, so you have a better lottery tickets, which has a good initialization for each task. So that kind of dilutes the curriculum learning effects, which works as a giving you a good initialization before you actually train on a specific task. However, there's like a one subfield where it still works, which is the RL, because you have reward sparsity. So still chunking into a different subtask and gives a lot more opportunity of getting having a gradient. The upset gradient descent can help you with the curriculum learning, and it's more effective. But one thing that I want to point out, and basically one thing that I'm mostly working in my PhD, is that often the curriculum so far has been thought in terms of between the data points. So you have the same task, so still like input-output function that you want to learn is the same, but the data points that you use for that learning is different. So it's either easy or difficult, you inject some noise and so on. But actually, in terms of continual learning or lifelong learning, the curriculum that we are interested in is between the task space. So you want to shift between multiple tasks, and curriculum in that regard is more interesting for people in this room, or in general, I think. So this task level curriculum and basically the adaptation that we can get to do more flexible generalization, I think, is a very, very interesting and important value. And there are a couple of literatures I want to cite. Again, Bell and Lawrence already show very simple case where it matters. And the new paper from ICML, from us, show that this primitive task curriculum, so you learn the first subtask, you learn first the subtask before you do the compositional task on top. You can analytically show that it can enable the faster compositional generalization. And also there is a paper from Jay McLand and Lampinen, which used this idea of meta mapping of the task representation. So you have this task representation, which tells you, for example, they use this card game as an example. So you generally have some information about how the card looks and what are the actions that you can take and so on. But you have a meta mapping of different card games, for example, poker. You can either win or lose poker, or there is, I don't know that many card games, but you know, whatever. And then you can basically use those meta card game representation to use this general understanding of the card games. So all of this works, I think. Sorry, I cannot. Can you just go? Yes, the next. So this was not working. Okay, so all of this, I think, points to the direction, okay, there is something around this, but I think understanding theoretical and controlled understanding of the different factors and how it affects it is quite understudied yet. And again, studying all these interactions and having a theoretical understanding will be important. All right.
So there's a question from the audience at home, actually. Yeah, if curriculum learning is marginal, isn't it contradictory to the task ordering effect affecting forgetting?
So that so exactly that's the point, because the curriculum learning is marginal. That paper from Itay was in this supervised image classification task, and the task is the same. You do the curriculum in the data space. So you give the easier data, which is, for example, less noisy, and then you go on to the difficult data, which is more noise. But in their setting, it's a different task. So that's what I meant by curriculum in data space versus the task space. So I don't think there is, so that's basically the point that I wanted to make, that we need to study the curriculum in task space, not the data space. Does that?
I hope. Another question was, someone said that they understand teacher-student network from a distillation point of view, but in this setting, they missed what is the role of the teacher. What problem does it solve?
Okay, so teacher doesn't give you any, so teacher is basically the problem that you want to solve. So because our goal is to have a model of the learning dynamics, and then to do that, we need to have a model, a task model basically where we know a solution, and that is the basic teacher, and the learning is basically student tries to become as similar as teacher. So yeah.
Thank you. Yeah, let's take a break until 11:50 and continue then.
So yeah, there is coffee and food right outside. Let's thank, meanwhile, our speakers. They will be back.